So I first of all want to talk about this test for divergence, okay? So we're going to talk about this test for divergence again because this is going to show up a bit more in 5.3. This is often a good starting point for determining whether or not a series will converge or diverge, okay? So our main goal is to determine whether a particular series is divergent. So how can I determine if a series is divergent? One way to do it is to just take the limit of the series or of the sequence. Meaning, why don't we just look at how all of the sequence terms behave? So if I don't even look to see what all of the terms add up to, maybe I could just tell if it diverges if I just look at the terms in the sequence. So what we're basically saying here is, if I can tell automatically that the limit doesn't exist, or if the limit just doesn't equal 0, okay, then I know that the series is automatically divergent. Well, that's really helpful. Really, really helpful. Because it's saying that if I take a limit and I get anything other than 0, the series automatically diverges. Let me say that again. If I'm trying to determine if a series diverges, and I look at the limit of just the sequence, if that sequence goes to anything but 0, then automatically the series will diverge. And there's a reason for that. Because the only way for me to add up a fixed number of answers to get a value is if those terms in a sequence keep getting smaller and go towards 0. But if those terms go towards anything else, then I'm just going to continue to add that number over and over and over and over infinitely, which means that the series is going to diverge. Okay? That's a really helpful tool, which says if I want to determine the limit of this series, let's start by just looking at the limit of the sequence. And because that was non-zero, I knew automatically that it diverged. Does anybody have any issues on that one? Okay, so this is a pretty helpful tool to sometimes just use as a starting point, because sometimes we get so overwhelmed by the different types of tests to use to determine if something converges or diverges that we bypass the most obvious choice, which is let's just take the limit of the sequence and see what happens. Okay. But what we're talking about mostly today is the integral test, okay? The integral test is pretty cool because it allows us to say if I want to determine the limit of a series, okay, if I want to determine whether or not a series converges or diverges, then why don't we look at the corresponding integral? Because a sum, a sigma, a summation, is a certain type of summation, and an integral is a certain type of summation, okay? So here's the idea. What if instead of trying to determine the sum of this, we tried instead to determine the integral of 1 over x squared dx. So look at the relationship here. Okay, they're both saying to go from 1 to infinity. They're both talking about basically the same function. It's just that here, it's not a function. This right here is a sequence, while this down here is a function. Okay, but notice we're basically saying that there are certain times where I could just convert this sum up top, this sum of a sequence, into an integral, calculate the integral, and the sequence will behave in the same way. But there's only certain criteria where that would happen. Okay, so I want to kind of go through this process here. Now let's just say that we wanted to discuss the convergence of this series. We know that by plugging in 1 and plugging in 2 and plugging in 3 and so on is going to give me a series that looks like this. okay? And if you were to look at a table of values for all of these, the sum seems to be getting closer and closer and closer and closer and closer and closer to some fixed value. Just by investigating the table, it looks like it's going to converge. But what tells me that it's going to converge? And so what tells me it's going to converge is by trying to think of the difference between this sum up here and this sum down here. All right, so let's just go ahead and first of all talk about the integral. Isn't the integral sum going to give me all of this area underneath this curve? It's going to give me the entire area bounded under, all the way down to the x-axis, right? So that's going to be the total area. That's going to be the integral from 1 to infinity of 1 over x squared. Now, if we compute this integral down here, okay, then we would notice that it converges. Okay, we're not going to do that yet, but basically, if we could show that the integral converges, then let's look at how I can guarantee that the sequence must also converge. Because isn't the sequence just going to essentially be this height plus this height plus this height plus this height? Because notice that all we're doing at this point is finding, let me try to explain this. All we're basically doing here is finding what the function value is at each of these locations. So really, the sum of the sequence is going to be just the sum of each of these rectangles. And so we're trying to interpret the fact that the sequence describes just the height values, while the integral describes every value, okay? So the entire area under the curve. And so with the integral test, we're going to be able to demonstrate that in certain circumstances, if the integral, okay, if the integral converges, then the corresponding sequence will converge as well. So let's just take a look at what this is equal to. This is 1 over 1 plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared. So it's just the rectangles, right? So now we want to focus on this, because if I were to get rid of the first rectangle, okay, which seems a little weird, but am I able to just cancel that out? Well, it turns out that, yeah, you are, okay, because if I were to do so, okay, then the area of the remaining rectangle is going to be smaller. The area of what remains is going to be smaller than whatever the total area from 1 to infinity is, plus that extra rectangle. Okay, so that must mean that this, and this is not obvious right now, so forget about this part. Don't look at that. Okay, so all we're saying then is that this sum will actually converge, because all it is just some extra constant or extra height plus whatever that integral is. And that integral converges, so the integral plus 1 will also converge. Okay, so this is kind of the I guess the theory behind the integral test, but it actually turns out practically to be a lot easier. So let's go ahead and state when the integral test is able to be used. Okay, so the integral test in general is basically saying if we have a positive function, meaning it's always above the x-axis, if we have a continuous function, meaning there's no breaks, and we have a decreasing function on 1 to infinity. Well, look at this. That's why we're saying every one of these integrals is going to be going from 1 to infinity. From 1 to infinity. That's what we're dealing with infinite series. And so we just want to make sure that from 1 to infinity, if we were to take a look at a graph, okay, if we were to look at a graph here, then we just need to make sure that the function is continuous, meaning no breaks. We need to also make sure that it is positive. That means completely above the x-axis. And we also need to make sure that it's decreasing, meaning getting smaller. Well, the only way to get smaller and still maintain positive is if it's approaching this horizontal asymptote. So that's why it satisfies all of the criteria, okay, that this type of sequence has to be continuous, no breaks, it has to be positive, completely above the x-axis, and it has to be decreasing. If these criteria are met, then and only then can I use the integral test. And the integral test says if you compute the integral and it converges, then the sequence must also, or the series must also converge. If you calculate the integral and it diverges, then the series must also diverge. So this is just saying that the series does the same thing that the corresponding integral does, which is pretty cool, because now we've got a method of being able to find the sum, or rather determine whether or not certain series converge or diverge. So one thing that we're going to start with is this idea of a p-series. We've already learned about geometric series. We've learned about telescoping series. We're now looking at p-series. And a p-series is going to be a series that looks like this. In other words, a series of 1 over n squared, or 1 over, well, n to the first, or 1 over the square root of n, that's n to the 1/2, or 1 over n to the 5th, or 1 over n to the -4, or any of these, right? These are considered p-series, okay? P-series will be convergent, meaning that they will give a fixed quantity if the p-value is greater than 1. Okay? If the p-value is greater than 1, then it converges. If the p-value is less than or equal to 1, it diverges. So we can see with this, 2 is greater than 1. So what does that mean?
Converges.
It converges. But wait a second, now we have n to the first. N is equal to 1. What does that mean?
It's harmonic, so it diverges.
It diverges, and from our video last night, it was a harmonic series. But now we recognize that this power is n to the 1/2. What do we notice there?
Diverges.
It diverges because that's less than 1. But wait, this is 5. That's greater than 1, so it converges. But this value right here is less than 1. So it diverges. So we can see really easily that if you see certain types of series that are just 1 over n to a power, we can see right away whether or not they converge or diverge. Okay? The videos last night show you why certain p-series converge while others diverge. What we want to basically do at this point is just be able to see that they either converge or diverge. Okay? Any questions on that? Okay. So why don't we do let's do okay. So why don't we try to think of a good one here. So let's just go ahead and do an example of, does the sum from n equals 1 to infinity of 1 over n cubed converge. Now we could cheat and just say, well, yeah, it obviously converges because it's a p series where p is greater than 1. Great, and that is exactly what we are eventually going to do. But I want to demonstrate why this is true for this particular series by using the integral test. So I want you to think about what 1 over n cubed looks like. Okay, 1 over n cubed is a decreasing function. When I plug in numbers from 1 to infinity, it's going to be positive. And I could also see that it is decreasing. So this is what 1 over x cubed looks like, right? Which means, because it satisfies the criteria that if f of x is equal to 1 over x cubed, then we could say that f is continuous, positive, and decreasing. Okay, so what we're basically showing here is that this criteria has to be met to even think to use the integral test. If you don't state that, then you're not using the integral test. Okay, you have to make sure that you state this criteria. So now that means that all we've got to do is find the integral from 1 to infinity of 1 over x cubed dx. Well, look at that. That's an improper integral. So before I can do that, I've got to rewrite this as a limit. So we write this as the limit as, let's call it t or b, as t approaches infinity of the integral from 1 to t of x to the negative 3 dx. Okay. Well, we can see at this point that this is still going to be a limit as t approaches infinity. But now when I integrate x to the negative 3, I get x to the negative 2 times 1 over negative 2. So I get the negative 1 over 2x squared. Only that's going to be evaluated from 1 to t. Okay. All right, well now when we evaluate this limit after using the fundamental theorem, this becomes negative 1 over 2t squared minus negative 1 over 2. But I hope that what you can notice is that anytime this is in fact convergent, this term will go to 0 when you plug in infinity, which means all that's left is going to show up from the second part, from the lower limit of integration in the fundamental theorem, which means that when I take the limit as t approaches infinity here, this gives me an answer of 1 over 2. So what does that tell me?
It converges.
It tells me that it converges. And so all that tells me then is that this series from n equals 1 to infinity of 1 over n cubed, I know that it converges. Cool on that?
So it converges to 1/2?
Good question. So does it converge to 1/2? What do you think? Is that what that says?
No, it just proves that it converges. It doesn't prove where it does converge to.
Okay. Because what did we just prove? We did just prove that the integral converges. So we just proved that all of this area underneath the curve, the entire area is going to converge to 1/2. The integral is not the same as the series. So by using the integral, I can see, first of all, that the integral, assuming that p is greater than 0, turns out is always going to converge to 1 over p minus 1, which is pretty cool, because if p is equal to 3 here, okay, so notice that p is equal to 3. Well, if p is equal to 3, 1 over 3 minus 1 is in fact 1/2. That's not coincidental. That's always going to be true. But notice that we are not saying that the series converges. All we are saying, or we're not saying that the series converges to 1 over p minus 1. We're saying only that the series converges. Okay, so that's all we could say. What does it converge to? I don't know. But we don't need to know. All we need to know is that it converges. Everybody all right with that? All right, so that's a demonstration of how we could use the integral test to be able to demonstrate convergence or divergence. If the integral converges for this criteria, assuming that you have a function that's continuous, positive, and decreasing, if the series converges, or I'm sorry, if the integral converges, then the series converges, and if the integral diverges, then the corresponding series diverges as well.